Now that we have the ability to calculate R, the correlation coefficient, and Y hat, the equation of best fit, the regression line for a data set, we can now use them to see just how well the data does match up, just how well there is a relationship between the two data sets. First off, we're going to look at what's called the coefficient of determination. It's the square of the correlation coefficient, so basically it's just R squared. This gives a percentage of the variation of Y that can be explained by the relationship between X and Y. For example, when R equals 0.801, for the percentage increase in the number of Nobel laureates versus the percentage increase in the consumption of chocolate by a country, R squared equals 0.642, which means 64.2% of the variation in the increase in Nobel laureates can be explained by that relationship between Nobel laureates and the consumption of chocolates. While the rest, 1 minus R squared, 35.8%, cannot, and is likely due to other factors, which could include sampling error, coincidence, or lurking variables. Remember, lurking variables are variables that may affect your data but aren't actually part of the data that's being studied. There is another way to figure out R squared, and that is it is the ratio of the explained variation divided by the total variation. Now, the total variation is the sum of the squares of the differences between the Y value. So when you see yi, that's the actual value that was in your ordered pair, your data sets, the Y value, and the mean of Y. The explained variation is the sum of the squares of the difference between each predicted Y value from the regression equation and the mean of Y. So total is actual data value Y's in your data set, whereas the explained, those are from the regression equation. And then the unexplained part is basically your residuals, which is the data value you had in your data set, subtract the one that came from the regression equation, and then again it's the sum of the squares for each ordered pair and each corresponding predicted Y value. Please note that the total variation should equal the explained variation plus the unexplained variation. Now, once we have all that information, we can find what's called the standard error of estimate, SE. It's basically the standard deviation of the observed Y values about the predicted Y hat value for a given X value. The standard error of the estimate is the square root of the unexplained. So it's using this one. It's the unexplained variation divided by n minus 2. The reason for the n minus 2 is you have both X and Y. So in terms of degree of freedoms, you have to subtract 2. And n is the number of pairs of data. There are two equations for this, one of which is the sum of the squares of the differences between the Y values and the predicted Y values. And then here we have the sum of the Y squareds, sum of the Y's, sum of the XY's, and then note we have the B naught and the B1. B1 again is the slope of your regression line from your regression line. Now, if we are given a regression equation, okay, so we have already calculated our regression equation, and then we're also given a specific value of X, and it does not necessarily have to be one of the X values in your original data set, but you do have to specify this ahead of time, a specific value of X, then we can make basically a confidence interval. We call it a C prediction interval for Y, and note basically what we're doing is we're using Y hat as our point estimate for Y, and then we have to figure out a margin of error to create that prediction interval. And basically this is where the probability the prediction interval contains Y is C. C is the level of confidence. So you'll see problems that will say things like, with a 90% confidence, construct the prediction interval. Now, the margin of error equation is a little bit more complicated than some of the ones we've had in the past. First off, TC here. The TC is the critical T-score, so you got to use table 5 and 2 degrees of freedom for that. And then we have, please note, N, that's the number of pairs in your sample. X0 is the particular X value that we brought in. Subtract the mean of the X values, and then in the denominator, similar to what we had for B1 and B0 earlier in the regression line, N times the sum of the X squared, subtract the sum of the X's squared. X and Y are required to have bivariate normal distributions. Basically what that means is for any value of X, the corresponding Y values are normally distributed, and for any value of Y, the corresponding values of X are normally distributed. Now you might say, what do you mean values? Isn't there just one X for one Y? But you have to remember that what you're really using in all of these things is the idea of this is a sample. And then can you make any inferences about a population from your sample? And of course, since it's just a sample, if I collect another sample, I'll have slightly different values. And so that's why you have to talk about, for a particular value of X, all the corresponding Y values depending on one sample from the next. For any value of Y, all the corresponding X values are normally distributed. And then finally, note regression equations are determined using random samples, as I just mentioned, and the prediction interval is constructed for the true value of Y. For X values near the mean, X bar, the prediction interval becomes narrower, but it becomes wider when the X values are far from X bar. On the other hand, it's also true that when you're building your confidence intervals, depending on, do I want a, 95% confidence or a 99% confidence, you'll find that your intervals are wider than if you had said, I'll only have 80 or something like that, because they come in with your critical T-score. But to sum up, this is why regression equations should not be used to predict Y values for X values that are outside the range of observed data values. So it's much more that you want to pick something that's interpolating within than extrapolating without. All right, so let's go back to our chocolate versus Nobel laureates again. It saves us a lot of time and effort because we already have a whole bunch of things that are already calculated. Now, a few additional columns that we haven't seen before. So let me go over it. The first few columns are all the same, X, Y, X squared, Y squared, and XY, so that we can sum them up and use them in whatever equations we need to. But now, this column, Y hat, that came from plugging in the different X values into this equation. Okay, so this is the same equation that we found in the last section. Then, here are the residuals. The Y values subtract the X values. So 5.5 subtract 7.9 gives us negative 2.4. 24.3 subtract 22.1 gives us 2.2. So this column here would be the residuals. Then we have our Y values subtract the means. So these are all difference from the means. And then this is how far the predicted values, the Y hats, are from the means. And then these last three columns are the squares of those things. So we have the square of the difference of the y values from the mean. We have the square of the differences between the y hat and the mean. And then we have the differences between the initial y values and the predicted y values. And anytime I say predicted y values, that means it came out of the equation. So, all of this we had before. And then now that I have these three columns, sum of the squares, I can go ahead and sum up these columns and to get what their values are. And if you kind of visually glance, you don't really need to get a calculator out, but you can see that 2294 is going to be pretty close to 1470 and the 823.6. So these two add to give you that one. And then also from section 2, we had section 1 we had our correlation coefficient, and section 2 we had what was our equation. These of course are the same things that we had at the top of the page to do our y hat or our predicted values of y. So now we get to, let's determine some things in section 3. First off, coefficient of determination, that's r squared. So if we take the 0.80061 and square it, we get 0.641. What is the total variation? Well, the total variation is just the sum of the squares of the differences from the y values and the mean of the y values. The explained variation, well, that's just the sum of the squares of the differences between the predicted values of y and the mean of y. And then the unexplained variation, well, those are the sum of the squares of the differences between our data set y values and our predicted y values. In other words, these are the residuals squared and then summed. So, a second way, if we already had r, we just square it, but please note here, r squared is also the explained variation divided by the total variation. And so when we plug in the two numbers, we come out basically with our 0.641 again. So really, more than saying that this is a different way of calculating r squared, it's more to show you that when we do r squared from having r, it is also telling us the ratio of the explained variation versus the total variation. Alright, so let's look at some data now to do these. Oh, we want to do standard errors, before we move on to another data set. So find the standard area for the estimate of the chocolate Nobel laureate data. And so now we're using those residuals, yi minus y hat I. Those are the residuals squared, summed, and then over n minus 2 square rooted. And we get a standard error of 6.263. So that's like the standard deviation of the residual differences of the residuals. And then we have a second way that we can do it. And basically, if you plug in all the numbers, it's pretty darn close. Again, any difference is probably due to rounding. But, for 2 decimal places, anyway, they were exactly the same. Now let's go ahead and construct a 95% prediction interval for the percent increases. We do have our equation, and we're going to use 6% as the increase in chocolate consumption as our x0 value. So, again, what we're going to do is try to create a prediction interval for where the true value of y would fall in between those two. Here is our margin of error equation. Since we have n of 23, that means the degrees of freedom is 21. So when we use table 5, we need to look at row 21. The confidence level is 95%. So that means our alpha is 0.05 and 2 tails. So that tells us what column to look at. So looking at those columns, let me see if I can grab the t-distribution real quick so that you can see. So we're looking here at 21, and then at the top, 0.05 and 2 tails. And so you can see, the 2.08, this has 796, but, if you've rounded it to the third decimal place, it would be 2.080. So that's where that comes from. Now, up here we found the standard error of 6.263 from problem 1. We already had, and this is from previous problems, we had the mean, the sum of the x's, sum of the x squareds. So now we can go ahead, and so please note, I can't do my margin of error unless I've already done my standard error estimate. So here's my equation again for the chocolate and Nobel laureates. I plugged in my 6 for the 6%. 11.591 is what my predicted value of y is. So that will be my point estimate for my interval. Again, it's going to be y hat minus e and y hat plus e. So e equals all this, 2.080 for the t-score, 6.263 for the standard error. Plug in all the different numbers here using our mean, our sum of x's, our sum of x squareds, and we end up with a margin of error of 13.3. So my interval, 11.591, subtract the 13.3, 11.591 plus the 13.3 is my interval. So what we're saying, we are 95% confident that the true value of y will fall within this interval for an x of 6%. If we go back to the original data, it's not that easy necessarily to see. Like here is a 6, and we came out with a 9. Here's a 6.4, and we came out with a 31. 31 would have been too high for this. So, some of the values in the data set were very, very high. 5.3, we came out at 10.8. 4.5, 11.4. 4.5, 5.5. So, somewhere within that interval should be the true value of y with 95% confidence. So that's the idea in this section. We've already got our regression line, so we can find things out like r squared, the coefficient of determination. We can find out the standard error of estimate, and we can construct a prediction interval for where the true value of y. In other words, we had a sample, but we're trying to pick the true value of y for the population. So let's run through these again for a slightly smaller data set. Let you just see them all one more time. So we're back to our GDP versus CO2 emissions. Smaller data set, already have our equation from section 2. And again, x, y, x squared, y, xy, all this stuff I did in Excel. The y hats come by using the x's in our equation. Then we have our differentials between the y values and the y hat values. We have the differentials between the y values and our y bars, and then the predicted y values versus the means, the y bars, and then we have the squares of them, and then again we can have the sum of the squares for those different things. So really one way to look at it this is, basically all of that information that I've covered, that I haven't covered up now, this was all that we found before when we were finding our regression line. And then now that we have that, we can go ahead, find our residuals, and find out all this other information. And I just let Excel do it all. Alright, now that we have that, just as we did before, we can go ahead and find the coefficient of determination, r squared. Again, our r was 0.8736, so we square it and we get 76.763, which is saying 76.3% of the data can be explained by the relationship between GDP and CO2 emissions. Here's the total variation, the explained variation, and the unexplained variation. And again, just to go back, these are the same ones that I have over here that came from summing all those values for all the different XY pairs that we had. And we got the same r squared in both cases. So, find the standard error. And again, this is this one right here. So it is the sum of the squares of the residuals divided by n minus 2, square rooted. This one comes out a standard error estimate of 141.9. If we wanted to find it the other way by using the sum of the y squared, the sum of y, and the sum of the xy's, and our b0 and b1, we could. It is slightly different, but again, it's probably just due to how the numbers were rounded. I mean, these look like a lot of digits, but in terms of decimal places, we don't have that many. Alright, so now that I have my standard error of estimate, I can go ahead and construct we're going to do a 90% this time. A 90% prediction interval for CO2 emissions when the GDP is 2.8. Again, that was not one of the values in our data set, but it is within the data set. So, 2.8, we have a 3, a 4.6, a 3.9, so 2.8 definitely falls within that data set. So, let's see, n is 10, so degrees of freedom is 8. Confidence level of 90% means alpha is 0.1 and 2 tails. So when I go use table 5, row 8, 0.1, we get with a 1.860 from table 5 for the critical t-score. From problem 5, where we had our standard error, and then from problem 4 before, where we had the mean and sum of the x's, sum of the x squareds. So we can go ahead, plug all those numbers in to find E. In this case, E came out 279.376. So, y hat, the point estimate, the y hat for this was 614. So 614 subtract the 279, 614 plus the 279, and here is our interval. And so we would say we have a 90% confidence that the value of y will be in here for an x value of 2.8 trillion in GDP. And that is section 3.